This 2-bit adder is made of 5-volt relays, simple on-off switches, and light bulbs, designed using the logic gates and OR, as well as exclusive OR. Each switch and each bulb represent 1 bit, which is either on or off. The result of this full adder feeds into a second adder, and then to the bulbs to display the sum. Here is a list of the 17 test cases we will input into the machine. Test case 0.0. 0 plus 0 equals 0, which has all switches off, and no bulbs illuminated. Test case 0.1. 0 plus 1 equals 1. Test case 0.2. 0 plus 2 equals 2. Test case 0.3. 0 plus 3 equals 3. Test case 1.0. 1 plus 0 equals 1. Test case 1.1. 1 plus 1 equals 2. Test case 1.2. 1 plus 2 equals 3. Test case 1.3. 1 plus 3 equals 4. Test case 2.0. 2 plus 0 equals 2. Test case 2.1. 2 plus 1 equals 3. Test case 2.2. 2 plus 2 equals 4. Test case 2.3. 2 plus 3 equals 5. Test case 3.0. 3 plus 0 equals 3. Test case 3.1. 3 plus 1 equals 4. Test case 3.2. 3 plus 2 equals 5. Test case 3.3. 3 plus 3 equals 6. And the last test case, using the extra carry switch in the lower right corner, gives us 1 plus 3 equals 7. The truth tables for the logic gates are listed as such. Logical AND is only true if inputs A and B are both true, otherwise the result is false. For example, to make ice, you must have water, and also the temperature must be cold enough for the water to freeze. For logical OR, it is okay for both A and B to be true, but it is not a requirement. As long as one is true, then the result will also be true. For example, as long as you have either a bike or a car, then you are able to travel. Finally, exclusive OR dictates that inputs cannot both be true and cannot both be false, you must have only one or the other. For example, you may be permitted to order fish or chicken, but you cannot order both. This circuit diagram shows how the two half adders are joined by an OR gate to make a full adder with a carry. And in this diagram, we see how multiple adders can be linked to handle larger and larger numbers. In yet another chart, we can see our list of binary numbers and how many bulbs or bits would be needed to display a given number group. This can be described with the equation 2 to the power of x equals y, where x is the number of bulbs, and y is the size of the number group that you are able to display. Finally, we will look at our truth table analogies, as applied to the 4 test cases for a full adder. In example 1, both switches are off, so likewise all following results will be false, so the final output, or sum, will be 0. In example 2, A is 0, and B is 1, and the diagram shows the resulting sum of 1. In example 3, A is 1, and B is 0, and again the diagram shows the resulting sum of 1. And in example 4, both inputs are true, so the sum produced will be a 0 for the 1's place. However, this time the AND gate will produce a carry, so a 1 will be output for the 2's place, displaying the sum, 1 0, which represents the number 2 in binary.